Oh, I was gonna tell y'all on when I did back in chapter like 10b when we were doing that that truck problem, whether it can go over a bridge. There was a conversion I totally missed in that thing. I should have done a it's like a square feet or cubic feet to cubic inches that I should have done, and it's like you have to do the 3-dimensional thing, so it should have been like a factor of 12 to the third or something. So I was like a factor of, let's see, 1728, 1728. If you multiply the answer by that, it would like be correct, but it's like it's way off. But it's also like it was a bit putting the cart before the horse, putting chapter 10 before chapter 2, because it was a bunch of unit analysis stuff that we don't technically get into till now, right? And so let me swap over into my screen and then swap to my Droid cam. And that is blurry. That's probably a little better. This one, I can like go on and do it. I'm gonna try to zoom in on this a little bit. Well, I'll also move this over. Focus a little better. Well, I guess it'll have to work. Can you read that? Is it legible? Hopefully. How many buses are needed to transport 495 people if each bus holds 45 people? Someone responding?
So it's 495 divided by 45, right?
Uh-huh. That's pretty complicated.
Glad I got that right.
Think about 45 people for every one bus, right? The way that you could think about it. That would tell you to divide, right? So 495 divided by 45 is what?
11.
Yeah, so we need 11 buses.
All right.
What if there were 500 people? How many buses would you need?
Hold on.
We're getting like 11.11.
So wouldn't you just round it to 12?
You would have to round this up. So that's what I was trying to get at. Sometimes you have to think about the context of the problem.
So would it be 12 then instead of 11?
So you would have to round it up because you would be left over with like some portion of people here, right?
Yes.
If you told me 11 buses, there would be some people missing the bus.
You know, this is kind of weird because if this was like a decimal number, we would round it off and still stay 11.
Yeah.
But because we're talking about some objects, then it changes.
Yep.
That's weird. I'm like,
you just got to think about it. You got to look at the number and then you got to think about it, what it means relative to like what you're doing.
Yeah.
Numbers are good for representations, but we also got to know like what they're representing, right? So show clearly your use of units for the following calculations. A raised flower bed is 30 feet by 6 feet by 1.2 feet. Find the area of the bed in the volume of the soil it holds. So the area of the bed is what two things? What are they talking about?
Radius.
Base times height.
Should be length times width, right? I think that's what they're doing here. That would be the bed, and this would be the depth. So if they want to know the volume of the bed, they're talking about the length and the width of the bed. So it should be 30 times 60. Times 6. 180, and I didn't put it on here. Sheet. Horrible. This is feet. If we do 6 times 30, that's going to give me 180. And if I do feet times feet, this is going to be feet. What's the unit on this?
Squared.
Yeah, okay. Just making sure we're all together. So that's the area of the flower bed. And if we want the volume, then what are we doing? So we have done this already, so I'm hoping this is not going to be like something that's tripping you up too much, right?
Length times width times height.
Exactly. It's the 3 things multiplied together. So it's going to be that 180 times 1.2. I didn't do this yet. Let me get 180 times 1.2 is what, 216? I think is what I'm getting for the number. And what's my units on here?
Feet cubed.
Yeah.
Oh, yeah, cubed.
And hopefully that makes sense, because if we have 3 things multiplied together, that's something being cubed, right? Just like x squared is like x times or something like that, right? 2 times.
So did I got 216 to the third. You got, okay, so that's how I gotta do it. Feet. I keep forgetting that.
Okay.
I gotta take that. Okay.
25. About these, I think these are pretty much like a review for the most part. 24 is pretty straightforward. You could overcomplicate it like I did, but you don't necessarily have to.
Can I say just 216?
If you do, you're going to get some points off for not putting your units.
The 3?
You got to put your units.
All right.
You got to know what dimensions it's in.
All right.
You're right. The area is going to be in 2nd dimension. Volume is going to be in 3rd dimension.
Okay. Volume's 3rd dimension.
Okay. That is what, 24, 25. We didn't do 27. Your average speed on a bike. So, okay, let's read the instructions first, probably. Identifying units. Identify the units of the following quantities. State the units mathematically, for example, miles dash hours, or in words, for example, miles per hour. So we'll probably do both. Your average speed on a bike. Oh, Jesus. I don't even want to read this. Your average speed on a bike found by dividing distance traveled in miles by elapsed time in hours. What do you think what measurement is that going to be?
Okay.
So if you're going to do speed,
Miles per hour.
yeah, it's so horrible. Miles
Sorry,
per
my
hour.
mic was muted.
Mhm.
I hope that's pretty straightforward, but there is this thing that sometimes they say distance equals rate times time. And so I think y'all kind of know this already. If I'm going 60 miles and I'm doing that for like what, 1 hour? Or if I'm going 60 miles per hour and I'm doing that for 1 hour, how far have I driven? I've driven 60 miles, right? And if I do 2 hours, I'm going to drive 120 miles. So I know I just answered my own question. But I'm sure most people would be able to answer that, I think. Like if I'm driving 60 miles per hour for 3 hours, that's going to be 180 miles. I can't even speak anymore. 180 miles. Sorry. And so there's this relationship like distance equals rate times time. And if you think about your units, that should make a little bit of sense, because if we're doing miles divided by hours, and you multiply by the thing called hours, we're going to end up with something in miles. Okay, so the word per means divide, right? And I think I went over that before, hopefully in the notes somewhere. That and of, right, means multiply. How much would you pay for 2.5 ounces of gold at a price of $1,200 per ounce?
3,000.
Yeah, this. We take what? We take 1,200 per ounce. 1,200 per ounce, and figuring out how much 2.5 ounces we need. Simplifying out our units. Whew, I'm like, you can't see what I'm writing. Here we go.
And your mic was out.
My mic is going in and out.
Oh, so that's
Yes.
1,000.
Yes, your mic is going in and out bad.
Yeah.
Oh man. God. Why is it doing that? If I talk nicely to my computer, you think you'll quit? Okay. And so hopefully what you're doing is 2.5 times the 1,200 will give you the 3,000.
1,200 times 2. And then 1,200.
And if
Divided by
it helps you to put over 1, you can put over 1. But that over 1, like I'm never gonna put that again, probably. If I just see a 1 on the bottom, I'm probably just jumping to whatever the heck is on top, which is $3,000. Sorry, this thing should probably have a dollar sign on it still, huh? Other questions about this? Can y'all hear me now? Sorry. Oh man. Yeah, let's not do that commercial. I'm glad they don't have those commercials anymore, do they? With the was it Verizon that used to do that? Can you hear me now?
Yeah.
Yeah. Here we are on 39. If your car gets 32 miles per gallon, how much does it cost you to drive 30 miles when gas costs $2.55 per gallon? So what should we start with? You can start with anything, to be honest. You could do this totally disorganized and it will come up some way or another. If we just write things out correctly. Like I don't know, let's just do it. 32 miles per gallon means 32 miles and I divide it by what gallons. And the next thing they give me is something with we're driving 30 miles. So if I want to do 30 miles, I know what my miles. So I want to write them like catty corner, right? Opposite. Probably can come up backwards or upside down, but it will still work. You just have to keep it like going along, maybe $2.55 per gallon. So I know gallons is down here. I want gallons up here. For every 1 gallon, it's going to cost me $2.55.
Sir,
Yeah.
your whole explanation of that, like your mic was out.
Oh man. Yeah, I don't know what to. I'm not really sure what to do. I could, if it gets disconnected, I guess we can all pile back up in here. But I could try to maybe reconnect it. See if that fixes it. If this just disconnects the Zoom, then come back. But I don't know what else to tell you. Let's see.
The gallon is.
Okay, can y'all hear me now?
Yes.
All right, good. Because, well, shoot, send my internet connection's unstable. I redid my internet connection. So, like I said, if you don't know how this is done, if you just set things up so that things will simplify and cross out, it will still work.
So is that middle one 3.785 liters? Because that's gallons, and then you got liters, and you got miles on the other side. You got gallons and per gallons on the end. I mean,
I don't see liters anywhere in this problem.
Oh, well, that's how much a gallon is. 3.785 liters.
Yeah, we're not doing liters. It's not coming up. Not coming up.
Okay.
We're doing 32 miles per gallon. This gives us 30 miles, and it gives us 255 for every 1 gallon. So this is okay. It's not written the correct sort of way. We should really flip things is what we should really do, because this is going to end up giving us something in the dollars on the bottom, right?
Mhm.
And so things weren't written correctly. And if you wanted to, you could do 1 here, because if things were written correctly, it should have been 30 over 1 miles, right? But it will still come up correctly. We'll still have 30 times 2.55 on bottom. Gives me something like what, 76.5. And so now you can like flip these things. So if you mess it up and you don't write things in the right order, and like one of the key indicators is things aren't in the right order is that my units are coming up on bottom, right? So I want to end up with dollars, but my dollars was on bottom. So now if I flip it, my dollars is on top. So you can fix these things if you mess up how you arrange them, is what I'm trying to do. I'm not trying to mess this up on purpose. Well, I kind of am, is what I mean. I'm trying to mess it up on purpose to kind of show you, you can still fix it. And if I do this, it rounds to 239. The way you should have done it, and let me do this again right quick. I'm going to do this really quick. We get 30 miles over 1. We get 32 miles. One gallon is 255. And this would arrange things in the right order. So we would have 30 times 255 on top, and then we'd have the 32 on the bottom, which would give us back to this thing. So even if you arrange things like backwards or upside down, like you can still kind of salvage your problem if you just work smarter, not harder. I don't know. Right. Your units will tell you what you did, right? To some degree. If 35 over 39, 41. It came for $7.70 per pound. The piece you want to buy weighs 0.11 pounds. How much will it cost to the nearest cent? Okay, we're supposed to consider the following exam question and the student solutions. Determine whether each solution is correct. If it's not correct, explain why it's not correct. What would you do to do this without looking at their solution? And it's $7.70 per pound. What's the operation here? You probably just know this is 70 cents per pound and I want to buy this many pounds. What do I do with these two numbers?
Divide them.
If it's like 7 cents per apple and I'm buying 7 apples, what am I doing with those two numbers?
Multiplied it by 0.11 when I did it.
Should be multiplied, yeah. 0.11 and this should give me something that is in dollars. And if I do that, it's what, 0.847, so 0.85 is what they're probably going to end up charging. So rounding it up. So what did the student say? They said to divide it. And so why is that wrong? Because we should have multiplied that thing, right? And so if you write out your units, if you write out your unit analysis, you don't really have to worry about whether you're like multiplying or dividing things. It will tell you. But there's also that thing, if we go like what? Big to small, multiply all, small to big, divide to big. That works for conversions. That doesn't really work for this section too much. Okay, so that is 6 of them. We're at a top 115. An air conditioning system can circulate 350 cubic feet of air per minute. How many cubic yards of air can it circulate per minute? So my suggestion on this is to write that unit thing out. They're telling us 350 cubic feet. But what does cubic feet look like? And I want it expanded, like, if that makes sense, hopefully.
Is it
Feet times feet times feet.
That's exactly what I want to see. Times feet times feet. 1 yard is 3 feet, is what we're doing. So if we want to get rid of these feet, where do I have to put my feet over here? On the floorboard. You could always do this thing over 1 if you want. But these things are on top, so where do I have to put the feet over here?
on the bottom?
So I want to go from
On the
feet,
bottom.
and I want to go from feet to yards. And so what did I say? 1 yard is 3 feet. Is that what the thing is? So you got to be sure to put that the right way. 1 yard is 3 feet. And I did it once. How many times am I going to have to do this?
3 times.
3 times. I'm going to do this guy 3 times. Every time is 1 yard or 3 feet. I'm going to take this place. Here we go. There are a few ways to do this, but on top, usually what we're going to do is multiply straight across, and then divide. So this feet and this feet, this feet and this feet, this feet and this feet are no more. On top, we have 350. On bottom, we have 3 times 3 times 3 is going to give me
Times 3, 27.
27. And on top, I have the units of yards times yards times yards. And so I'm taking 350, I'm dividing it by 27. Did I say how word around it?
Jesus.
It doesn't say word around it. I'm probably going to round it to 3 decimal places. Where am I at? 963. I want to write those yards 3 times again. So this is going back to that thing I was talking about previously when we were doing the chapter 10b, but we kind of glossed over it maybe a little bit. But if I'm doing something with volume that is in 3 dimensions and I'm tripling a 1 dimension, then in 3 dimensions, it's going to be a factor of 27 is what this is saying, right? If I was doing area, it would be a factor of like 9. It'd be 3 squared. So you have to be careful like with what dimension you're in and with these conversion factors. And I think this comes up later too when we actually do chapter 3b or 2b, sorry. Yeah. 2b or not to be. So that was what, 59? I think we're on what, 61 now? Oh man, I didn't even pull up that table. So this is the table. You're in dinner in London, cost 82 British pounds. we've got 82 British pounds. We want to figure out what that thing is. These are the currency rates that they're giving us. And I said, look, what's the number? We're looking here. I want to convert this to dollars. They're giving me pounds. So I can think of this pounds as being on top. And so if pounds is on top and I want to convert it, where am I going to put pounds over here?
The bottom.
On the bottom. So this is my pounds, then this has to be my dollars. There are two different ways you can do this. What is the number I should put up here?
1.
You can
One.
put 1 here. And if I put 1 there, what number should I put down here?
0.8191.
That is absolutely one way you can do it. There's another way you can do it.
I put the 1221 on the top.
Yes, that should also work. That's the other way. You put the 1.221 on top, then you put 1 on bottom, hopefully.
Yeah, that's what I do. Yeah.
So either way, you should be getting the same thing or something pretty close. If I do 82, let me double check. 0.8191 gives me 100.109. So you're a little bit off, like maybe a little bit. That's a rounding error. So 100.12, 100.11, right? You're a cent off. I'm not going to count anything off for being a cent off, right?
Okay. I got 100, 10. That's crazy.
From my understanding, that's like, this is something you actually probably want to check when you like do currency conversions in certain countries. A lot of those like tourist traps, they don't give you like the appropriate rate for like what you transfer.
For some reason, I'm getting 104 cents, 100.04
For which one?
for the pounds to dollars.
82 times 1.221. Did you do multiplying or dividing?
Multiply.
So it should be 82 times 1.221, right?
Right.
So it should
I'm
be-
not adding in the 1, I don't think.
okay. Oh. Coffee is the nectar of the gods. Okay. So I think we have another euros per liter problem. And they give us gallons to liter conversion. So that's nice because I wouldn't know that off the top of my head. I have to go look that up. But gasoline, we read that gasoline sells for 1.5 euros per liter. Euros for every. If I don't know it, I always put 1, right? So it's 1.5 euros for every 1 liter that we're buying. We want to know dollars per gallon. Are you converting the euros or the liters? I guess is the question.
The liters.
You want to go for the liters? So if liters is down here, where am I going to put liters over here?
On top.
On top.
Yes. And we're going to go for liters too? Gallons. And if I want to do this, I got to write this correctly. 785 liters. They tell me. I like hearing a bunch of different voices. It's always nice. All right, so I could do that. That will get me my liters and gallons. If you want to do this one thing at a time, that's the thing you can do. I'm going to do this all at once. So now I want to get rid of my euros. I know euros over here are on top. If I want to get rid of euros, where am I putting my euros over here?
Bottom.
On the bottom. So my euros have to go on bottom here. I'm going from euros to dollars. I'm going to have to go look at my chart. European euro. So this, again, there are two different ways you can do this. But this is dollars for foreign. This is foreign per dollars. And I didn't say it, but this is like many dollars for every.
So we're taking 1.058. Yeah.
Dollars for every one cap. And this is the exact opposite. This means there is pounds for every one. So the euro,
1 point.
what am I putting on top?
1.
1.058.
Yeah, it's fine. You can put that one on top, $1.058 for every 1 euro that we're doing. Or you could put the 0.994, the 0.9449 on bottom, right? Those are reciprocals of each other. I talked a little bit about that in the notes. But it looks like we got 3 different numbers to multiply together. This euros and those euros we can mark through. But we should be ending up with something in what units? Can we see the units on there?
Gallons.
Gallons is on bottom.
Dollars per gallon.
Dollars per gallon. Is that what they asked? I think that's what they asked. 1.5 times 3.785 times 1.058 is going to give me 6.006795, 6.01 is what I'm going to round it up to. So it's getting rounded up to 6.01 for every 1 gallon. Or you can say $601 per gallon. Or if you really wanted to be spiffy, you could go to what, 3 places and do the 9/10 of a cent thing that they always do on the gas pump. But we're not doing that. I always find that kind of weird. They go to like a 1/10 of a cent or whatever. I'm not sure why. Don't ask. I couldn't answer that. I know gas prices are kind of weird because they're not actually the price of gas. It's built on speculation on what they think the gas is worth. Okay, so where are we at? We did that, did that one. Did some currency conversion with gallons to liters. Now we are on 74. So we have this problem. I think I do this. Yeah. Suppose your car averages 38 miles per gallon on the highway if you're driving 55 miles per hour, and it averages 32 if you're driving. What is the driving time for a 2,000-mile trip if you drive an average of 55, and what is the driving time driving 70 miles per hour? So probably without doing unit analysis, you might be able to do this one. But if we want to do unit analysis, so this one might be a little weird because this says I have 55 miles for every 1 hour. And we want to set this up for what? A 2,000-mile trip. I guess I set that up backwards of what I probably should, but it'll still give you the right solution. But before you even did this chapter, you could probably tell me if I'm doing 2,000-mile trip and I want to go 55 miles per hour. The thing that I do with those two numbers is what?
You divide them?
Yeah, and this is that distance equals rate times time, right? This is my distance. Do you know what I'm talking about? A distance equals rate times time. Look at this thing. Distance equals rate times time. Is going to be my rate, which is what, 55 times my time. So if I want to find time, I have to divide by my rate, which is 55, right? This is another way we can think about this. Divide 55 by time. What is that? 2,000 divided by 55 is 36.36, repeating. We are talking about hours when we're talking about time in this problem. We're going miles and hours. Miles is our distance. Miles per hour is our rate. Our time is in hours. And what about driving 70? I'm getting something like what, 28.57? At 70. Does everyone know where I'm getting this thing from? Hopefully.
Yes.
2,000 divided by 70, right, is what I'm doing. Same thing as the previous thing. So assume a gasoline price of $2.55 per gallon. What is the gasoline cost for a 2,000-mile trip if you drive an average speed of 55? What is the gasoline cost at 70 miles per hour? So what is the information they're giving us? We can kind of start things up. $255 per gallon. And there's really two sort of things I need to figure out. Set 55 and at 70 miles per hour, right? I'm thinking at 55 miles per hour, it's getting 38 miles for every 1 gallon. And at 70, it's getting, what does it say? 32 miles. Okay. So now I'm looking at this. So if you want to know like what you want to end up with is money, right? So I think I might need to flip this thing. I need to end up with money on top. So if you want to flip, set things up correctly and not have to worry about flipping them, we want to end up with money on top. So a good sort of approach is to put money on top. So if I say $255 for every 1 gallon, what I want to get rid of is this thing called gallons. If I want to get rid of gallons, I have to multiply this by. And if gallons is on bottom here, where's gallons going to go over here?
On top.
Yeah, so gallons should come over here. And I'm not leaving myself nearly enough space because I'm going to have to do another first. But I know gallons to miles. I know that this thing will get 38 miles for every 1 gallon. So in the problem, the way that they word it, they say like 38 miles per gallon or something, maybe. Underneath everything. Yeah, they do give it to you like that, right? But when we're actually using it in the problem, we actually have to flip this thing, right? So hopefully that's not something that's going to trip you up too much. But now we're getting in what, in dollars per mile is what we're in now. Now we want to get rid of these miles. So how many miles does it say that we're going?
70.
Say 70? There's still doing a 2,000-mile trip.
70.
And 70 miles per hour is the other thing. We're in the 55 miles per hour right now. But they say we're going 2,000 miles, I believe, right? That's what the gasoline costs for a 2,000-mile trip. And so the unit miles, if I don't have a number, I can always put something over one. And this should simplify out my miles. And I should be left with something that is in doll hairs. So what am I getting? I'm getting 255 times 2,000 on top. 100 over 38. Cost me something like 134.21. Okay, so that was a lot of work for one problem, but the good sort of thing is you've set this up for the next thing, hopefully. So is this going to change in the next one, the 255 per gallon?
No.
No, that's going to stay the same. Gas price is still going to be the same. Is this thing going to change? The 1 gallon getting 38 miles?
Yes.
Yes, that's the thing that's going to change. Instead of 38, now we're going down to 32 miles for every 1 gallon. And then the last thing, I know I'm like, y'all can't see it. I'm going to move it up in just a second. The last thing, the 2,000 miles, is that going to change at all? It should not. We're still doing the same trip. So most of this should be the same, except the miles per gallon is changing, right? So I'm still going to get 2,000 times 2.55 on top. It's going to give me the 5,100. And then I divide that by 32 instead of 38. And I should be getting 159.38 when I round up. It should be like 0.375. So again, we can check our units. This is gallons, gallons, miles. Miles should simplify out.
I can't believe it was that simple to figure out. This one had me up for a while the other night, man.
Yeah, I mean, like I said, even if you flip things, you just have to reflip them. I don't know how else to say it, right? Like, if you accidentally you end up with your units on bottom, that means you just have to flip things. So if you don't set them up right, as long as you set them up where your like units are catty corner and they simplify out, cancel out, like you're good. They just got to be on opposite ends, right? One's in the numerator and one's in the denominator. And that comes back, and I said it in the notes, but it comes back from that thing if we have 9 over 9, right? Or if we have x over x. It's the same thing over itself. This is a big fancy one. All these big fancy ones. when you multiply by 1, you're not doing anything. So it kind of disappears. It simplifies out. Okay. That was 74. I think this is the last one in this section, I believe, right? I think we're going on to the next section. Now I'm going to have to zoom out a little bit for this one. Put this with bigger font. Can we read this all? I think it'll fit in there. One cubic foot holds 7.48 gallons of water. 1 gallon of water weighs 8.33 pounds. Ooh, excuse me. How much does 6 cubic feet of water weigh in pounds and tons? Oh man, they're gonna make us convert from pounds to tons. I got this annoying word still here. Here we go. We got to use this horrible thing that you may or may not be able to read, but this is in your book, table 2.2. I got it out. We're going to use it in just a second. But here we go. Where'd my pen go? Where did I do that? Threw it up somewhere. 1 cubic foot of water. So 1 cubic foot. To what? 7.48 gallons of water is one sort of thing we can do. That's one conversion factor. I don't know if that's the right way. We might have to flip it. But this is what I'm sort of thinking. 1 cubic foot of water to 7.48 gallons. I'm thinking of like 1 gallon. I have no idea if these are the right way. 8 pounds. And then they say something about 6 cubic feet. So this is definitely not set up the right way. But these are sort of my factors that I'm looking at. So I want to know how much it weighs. So I know I'm going to need my pounds on top. So if I do this probably the smart way, 8.33 pounds is the first thing I'm going to think about. And I got 8.33 pounds for every 1 gallon of water. And so I have this one other conversion factor with gallons. This thing has gallons in it. So if I wanted to get rid of gallons with this gallons, where am I writing gallons over here?
Top.
Yep, write it on top. And on the bottom, I'm going to feet cube. So 1 foot cubed is 7.48 gallons of water. And then the last thing, I got to write these two opposite. I think we're multiplying these three things together. And if I do things right, this is gallons, gallons, this is feet cube. I should end up with something with pounds on top. So you always want your, like I said this earlier, but we always want our units to be on top. If they're not on top, we have to do the flip. Times 7.48. Okay. Losing it. I'm like, I'm recording this, right? Yep. What am I? 8.5 pounds. 8.504, I think is what it went to. Okay, and then 373.85. And I want to convert pounds to tons. So if pounds is over here, we can think about it being on top. So if we want to convert pounds, where's the pounds need to go over here? On bottom. I just make odd noises. Okay. So 1 pound Pounds on bottom, tons are on top. We want to go from pounds to tons. And maybe I ought to box this number because this was one of our solutions, right? Where's this table? 1 ton is 2,000 pounds. So 1 ton. So besides, if you're like shipping company, you wanted you to weigh stuff in tons. I'm not really sure why you would do this, because what we're gonna be getting is 373.85, and hopefully you can see it, but we're gonna end up dividing here. So 373.85 divided by 2,000. It's giving me something like 0.1869. Somewhere around there.
That's right.
And we're talking about now tons. I guess I should pluralize this pounds too, huh? LBS. Okay. Questions about this, about setting it up? How do you set it up? Oh man, are you gonna be scientists now? It's gonna be exciting. That's your brain wasn't. Okay, so your utility company charges 13 cents per kilowatt hour of electricity. What is the daily cost of keeping a 100-watt light bulb lit for 12 hours each day? How much will you save in a year if you replace the bulb with an LED bulb that provides the same amount of light using only 25 watts of power? So, well, it's not even divided. Let's just start. We want to think about 2 different things. So the first thing we want to think about is a 100-watt bulb lit for 12 hours each day for a year. So I think on this, they say assume there's 365 days in a year. They're not considering that quarter day that we throw in there for the leap year, but 365 is close enough. So if we are doing it for 12 hours a day, what does that mean? So they charge per kilowatt hour. So we want to find kilowatt hour. So this might be kind of silly, but we have watts and hours. What do we want to do with these 2 things to get to kilowatt hours? It may not be super obvious, but kilowatts, we can transfer this to kilowatts, or watts, we can transfer to kilowatts. If we want kilowatt hours, what does this mean? This hyphen, what is that operation?
Is it multiplication?
It is absolutely multiplication. So if we want to get to kilowatt hours, what we do is we multiply watts by hours. So if we have 100 watts and we multiply by 12 hours, we will be in watt hours. What hour is it? Sorry. We don't want watts. We want to get rid of watts, and we want to make watts into kilowatts. So this thing should give me my kilowatts hours. So there are, I believe, 1,000 watts in 1 kilowatt. So you have to write those numbers in the correct order. And so this should give me my kilowatt hours, 100 times 12 divided by 1,000. So 100 times 12, I'm dividing this by 1,000. So I should have, those watts will simplify. And I know this says hours times watts, but this is really the same thing as kilowatts times hours. So this should be 1.2 kilowatt hours. Is everyone seeing how I'm getting this kilowatt hours?
Yes.
And this is what for every day, right? I believe that would be the 12 hours per day. So daily they're using 1.2 kilowatt hours. Do we want to do yearly? The cost and then figure out the yearly, right? There's sort of like two approaches. There's multiple approaches, probably more than two. But if we want to do this and we want to know what it is yearly, then how do we do that?
What do you
Divide by 12.
If this is
Divide by
daily,
365.
divide by.
Multiply by 365.
Honestly, divide. If this is each day and they want to know for each year, what would it be?
Multiply.
It'd be multiplied, yeah. We could do it right quick if you want, but I didn't want to spend that much time doing that. 1.2 right per day.
365.
You'd multiply to get to the years, right? You're going to charge so much per each day. So if we want to know yearly, we have to multiply by 365. So multiply by what? 365 will give you 438 kilowatt hours per year. And the last thing, maybe you're doing 438 kilowatt hours per year. How much is that getting charged per year? Yeah, 13 cents per kilowatt hour. So how do I set that up? So if kilowatt hours is where up here, I have to put kilowatt hours down here. So 13 cents per kilowatt hour. I hope that one should be like maybe straightforward, right? If it's 13 cents per kilowatt hours, we're using 438 kilowatt hours. We're multiplying those two things, right? Just like whenever you're shopping at the grocery store, you have so many items and there's so much cost per item. Multiply those things. So this should be giving you like 56.94. And what is that talking about? What were we figuring out here?
How much the light bulb would cost for the year to
Yeah,
keep
this
on
is-
12 hour for a day?
Yeah. So this is for the 100-watt bulb for a year. So we're doing this for a year. What else? So they start off with a 100-watt bulb. What is the other thing? Is a 25-watt bulb? So how would this change for a 25-watt bulb? Because we already did a lot of work. I don't want to have to do a lot of more work.
You'd multiply it by 0.25 or 1/4 or 1/4.
I think you could do that. Yeah. I was going to say, like, come back to here. And I was hoping they could maybe see it right at this point. Instead of 100, I'm going to plug in what?
25.
25. So if you wanted to do that, if you want to do what he said, you could absolutely do that. That's because the numbers are pretty and 25 is a quarter of 100. So you may not always have that pretty of numbers. But if you wanted to save a little time, you could come back and do the same work. Instead, plug in 25. That's going to give me 0.3 kilowatt hours daily. I'm going to have to figure out what that is for the year. And so that's 109.5 kilowatt hours for the year. And then I have to figure out the cost of that for the year is going to give me 14,235. So 1424 should be my yearly cost. And this is the 25-watt bulb. Does that come out the same dividing it by 4? Yeah. There we go. And so they wanted to know what the savings was. We're almost there. And so if we wanted to know the savings, the last thing we do is what, 56? 94. And we subtract it from the other one. So the savings per year should be 4270 per year. When I subtract these two. Jesus. I think someone's breaking in or something. I don't know. It's loud. You didn't call the SWAT on me, did you? This is SWAT raid. Oh man, that'd be horrible.
So, so Professor, you divided the 1428 from 4270. I mean, from 25.
So we subtract this one from this one. To
Ah,
get these two to get the savings, right? This is the savings. How much you would save. So this is how much the 100-watt bulb would cost. This is how much the 25-watt bulb would cost. If we want to know how much we would save, it's the difference between the two. So that one, I don't know what to tell you. It's pretty elaborate, but it should be doable. Like, it might take you a minute to think it through. You might end up flipping your units or something, but you should be able to work through it.
I've got a question on whenever it comes to like dollar amounts or like that first question that we did, we always round up or round down.
So it depends on the context of the problem. You're not going to do like half a person or something, right? Or if you need an extra bus, then you need an extra bus sort of thing. But in the context of money, like if it's a 5 or higher, you round up, or if it's a 4 or lower, round down, like just normal sort of rules. If it's money, you round to 2 decimal places to the nearest cent. And in general, if you round to like 2 or 3 decimal places, you should be pretty safe for the most part. I'm not going to be a big stickler on like stuff like that, as long as it's reasonable. I'm more concerned with the work that you're doing than it being correct, than with the number being exactly precise. But with that said, you have to keep some accuracy when you're working along with the problem and like not rounding until the end. Because if you round in the beginning, things get off and they get off further and further typically. So that is utility company. We got 51. Where am I at? 2. Okay. Block of oak has a volume of 200 cubic centimeters and weighs 0.12 kilograms. What is the density? Will it float? What was that? Let's go put this back. I had it in the notes and I've been forgot it. Density of water is what, 1 kilogram per centimeter cube? Is that what I said?
0.12 kilograms.
Oh no, this is the second part. That's why I'm getting confused. Okay.
So when he says density, he means volume, correct?
Density means the compactness, describes compactness or crowding. So 1 gram per centimeter cube is the density of water. So 1 gram per centimeter cube. So they want to know the density of this thing. We want to go in grams per unit volume, right? And so the grams here is the 0.1 unit volume. The volume of this thing is 200 cubic centimeters. So it's in kilograms per centimeter cube. What do we want to convert it to compare it to water?
Grams?
Yeah, we're converting kilograms to grams, right? So how do we do that? Where am I putting kilograms over here?
You're putting kilograms on the bottom and then some grams on top.
Kilogram, I believe, is what it is. warm. 0.12 times 1,000. Working up a sweat doing math. 120 is what we should get on the top. And if you want things out, grams, 200 meters cubed. You might be able to tell me already. Is this going to sink or float before I even give you a number?
Going to sink.
It's a 50-50 shot on that answer, huh? Okay, so this is 0.6. Calculate it. And we know water is 1 gram per centimeter cubed. And so what's the rule? This is less dense than water. So if it's less dense than water, is it going to sink or float?
Float.
This should float. They all float down here. Okay. So we're comparing 0.6 is less than 1, right? The number on top is smaller than the number on the bottom. We're going to get a smaller number than 1. The number on top is larger. It's going to be vice versa, right? Well, that's what I was trying to look at earlier. But questions about this one, about how to figure this out? I think this is a good question. It's applicable. It's something you ought to be able to do. Determine whether something can sink or float. I would probably tell you water is 1 gram per centimeter cube. I don't expect you to memorize stuff. If there's a formula, if there's a conversion factor, if there's anything that like seems like memorization, I'm probably not going to expect it. There are a few things that we use enough that you should kind of sort of know at some point. And I don't really feel like that's quite as much a memorization thing as like if you were doing the work, you should have learned it. I don't know how to say it, but so the next one, where are we at? 73, 80, more. So when you take a bath, you fill the tub with halfway point, and the tub measures 6 feet by 3 feet by 2.5 feet. When you take a shower, use the shower head with a flow rate of 1.75 gallons per minute and spend 10 minutes in the shower. There are 7.5 gallons in 1 cubic foot. Do you use more water taking a shower or a bath? So, they give us bath information first. So if we're taking a bath, we want to figure out how much water we're using. What are we figuring out? What's the magic word I'm probably looking for? It's not area, it's not distance, it is
Volume.
yeah, we're looking for volume of the water. So if we want to know volume of the water, or 7.5 gallons. There's a conversion factor of 7.5 gallons in 1 cubic foot of water. So we want to know cubic feet of water. Divide what, 3 foot by 2.5 feet. Is that what it says? It's like half cut off. Who did this? Horrible. Okay. The whole bath is going to be 45 cubic feet. But what they say is that when you fill it up where? Halfway? Okay. questions about this? Does everyone see where I'm getting this from? The 22.5 cubic feet? And I want to know how many gallons this thing uses. They're giving me 7.5 gallons to 1 cubic foot. So if this is cubic feet, where am I writing cubic feet over here? I should be writing it on the bottom. So this is 1 gallon, 7.5 cubic foot. Sorry. 22.5 times what? 7.5. So a bath is going to take 168.75 gallons. Here we go. And then the next thing. What about taking a shower? So the shower head is a flow rate of 1.75 gallons per minute. So they tell us 1.75 gallons for every 1 minute. And I'm setting this stuff up kind of smart because I know I want to end up with something in gallons. So now I need to know just how much time it's going to take me to shower. What did they say about the shower? 10 minutes in the shower. That's a short shower. Who showers for 10 minutes? I guess if it's a quick one. You gotta scald the skin off for like at least 15 minutes, right? Okay, so anyway, if you set these things up correctly, this is like going the miles per hour for so many hours. This is the rate times the time. This should give me what, 17.5 gallons? That seems drastically different. That's the numbers they give. Okay. So which one is using more water, the bath or the shower?
The bath.
Yep, lots more gallons, right? Okay. Questions? Okay. How long would you need to shower in order to use as much water as you use taking the bath? So what they're asking is if we're using 168.75 gallons, how long will it take to use 168.75 gallons if you're going 1.75 gallons per minute? And so these are the two things that they're asking now in part B, or these are the two sort of like information things I'm hoping you pick out. They want to know how long it will take to use 168.75 gallons when we're going at a rate of 1.75 gallons per minute. So this is not set up at all in the correct order. If I want to end up with something in minutes, I should probably put 1 minute on top to like what, 1.75 gallons. And if I do that, now I want to simplify out gallons. This 168.75 gallons over 1. You can always put it over 1. And now if I do this, this should give me something in minutes. So what I'm doing with these two numbers is I'm dividing these two numbers, 168.75, and I'm dividing that by 1.75. And this is giving me 96.4 from that 8. Which is about like what, an hour and a half and 6 minutes? Okay. Questions about this one? It's part B. Part C, what are they asking now? Assuming your shower is in a bathtub, propose a non-mathematical way to compare in one experiment the amounts of water you use taking a shower in a bath. I don't know what the heck they're running on this one. Just being honest, I didn't look at the solutions for this one. I didn't realize I had this silly of question. I looked through these and I solved them mentally. Does anybody have a clue? Oh, okay. I know what they're saying. This is like when you're a kid and you're taking a shower and you kind of want to make it a bath, right? Does anybody know what I'm talking about? They're trying to do a non-mathematical way, but I mean, it's kind of silly you say it's not mathematical because it is mathematical. It's just not formal math, right? It's not symbolic math, but it's still math. You're doing geometry, right? Do you know what they're trying to get at here? How would you compare the amount of water you use in a shower versus a bath? You start taking a shower, and then you're gonna do what? Do the little kid thing where you like stop up the drain and you see how long it takes you to fill it up halfways. That's what they're talking about. So whatever you want to say for that problem, good enough. I don't care. Let's do 80. When the metric system was first proposed, the unit of area was one. I can't read it. 1 R equal to 100 metric hectare. Hectare is equal to 1,000.
You're cutting out.
Okay, so when the metric system was first proposed, the unit of area was the R, with 1 R equal 100 meters squared. Today, the accepted metric unit of area is 1 hectare, which is 1 hectare is 100 R. The unit is used around the world in forestry and agriculture. Using a power of 10, how many square meters are there in 1 hectare? So one thing that does come up in this section, and I kind of want to go over it real quick. Exponents and negative exponents. So 2 to the first is just a really silly way to write 2. So we want to talk about things to the 0 power. So if I'm going this way, what is the operation? If I go from 2 to 4, how do I get there?
You add 2.
And not adding. The operation here would be what?
Multiply by itself.
Multiply.
Yeah, multiplied by 2. So yeah, I know you can add 2 because it's 2. 2 is one of those numbers that adding 2 is the same as multiplying by 2. So maybe it's a bit of a trick question. Multiply 3 to go up. So for multiplying by 2 to go up, how are we going to go down? What's the opposite?
Divide.
Divide by 2. So if I divide 2 by 2, what am I going to, excuse me, what am I going to get?
1.
If I divide 3 by 3, what am I going to get? And if I divide 10 by 10, what am I going to get? And so everything to the 0 power, except for 0, we're not going to talk about 0 to the 0. That'll start some fights. But everything to the 0 power is 1, except for 0. If we talk about negative powers, we're going to take 1, we're going to divide it by 2. We're going to end up with 1 over 2. We're going to end up with 3 here. Same thing, we're going to end up with 1 or 0.1. So negative exponents. And if we do it again, we're going to do a half of a half is like a fourth, which is like 1 over 2 squared. Same thing here. If we do this, we're going to end up with a 9th, which is kind of like 1 over 3 squared. And so one way that we do exponents is if this is over 1, we flip them and we make them positive. So if you ever have negative exponents, flipping them into a denominator, making them positive, or if they're in the denominator, you flip them up into the numerator. So I don't know how deep we're going to go into that, but it might come up a little bit. The 10s are really going to come up because we're about to do metric and we're about to do scientific notation. But 1 over 10 squared would be 1, or 10 to the minus 2 would be 1 over 10 squared. 1 over 100, which is 0.01, right? Okay, and now we're going to talk a little bit about metrics, so hopefully this will come back around. When it was first proposed, we read all this. Using a power 10, how many square meters are there in 1 hectare?
Oh, man.
So we want to know square meters. So if we want to know square meters, starting with this on top, with square meters on top might be a good approach. So we know 100 meters squared is going to be one of these weird ass measurements, 1 R, whatever it is. I don't I still use it. Okay, so 1 R. And if we want to get rid of the R, where are we going to put it over here?
On the top.
So 100 R. Hectare. So it looks like what we're doing is 100 times 100. And this is going to be meters every 1 hectare. No, I haven't really done what they did. Said I got this number, but I really need to put this number at a 10 to the something power. So how do I put that as a 10 to the something power? 10 to the what power?
Fourth.
Should be 4th. All you do is you count the zeros, basically, right? 10 to the 4th. Maybe 1. The way to put it, right? Okay, so express what 1 kilometer squared in hectares. So this is what we got for part A. Meters. Let's do it. So I think we want to continue to use this thing. So we want to express something in hectares. So I want to start out with hectares on top. That's what I want to end up with. I know my conversion is 10 to the 4th meter square. If it helps you out, we can always rewrite this 1 hectare. This is 10. This is meters times meters is what meters is going to give me. So now I want to convert things. I want to know, express 1 kilometer squared in hectares. So I don't want meters. what I want are kilometers. So if I want to get rid of meters here, where are they going over here?
On the top?
Yeah, you gotta go on the top. Meters go on top. Kilometers are gonna go on the bottom. There are 1,000 meters for every 1 kilometer. And I'm not gonna do it till someone tells me. But what should I really do on this problem?
Eliminate your meters. No. No.
That gets rid of one of them. What am I gonna have to do?
Would you
You have to do
multiply
another
another
one.
meter so that it could cancel out? Multiply the second meter?
Multiply by another 1,000 meters. So you have to do that conversion twice. It is a square unit that we're converting. So it's going to happen twice. So we're doing 1,000 times 1,000. If you want to give it to me as a power of 10, it's like counting the zeros here, right? So that on top, what am I going to get? Is that a weird thing to ask?
Is it 10 to the power of 6?
That's absolutely what. 3 zeros here, I have 3 zeros here.
That's what I got. 10 to the power of 6.
You could write it out as a million or whatever the heck it is, right?
Okay.
But I'd rather see 10 to the power of 6. And this is going to go over 10 to the power of 4 is what was on bottom. And so
Right.
10 to the power of 6 there. And on bottom, it is kilometers by kilometers or kilometers squared. So now I'm looking at this thing. I can simplify this thing a little bit. There's a little bit of a shortcut I talked about.
Would you subtract the power 6 minus 4?
That's exactly what you do. 10 to the 6 minus 4. And this unit hectoliters per kilometer. And so what we have is actually 10 squared
10 to the second.
hectoliters for every 1 kilometer squared. So what we actually have is the number 100. There we go. So there is a bit of shortcut if you have the same base. And when we work in metric and we work in scientific, we will have the same base quite a bit because they're both base 10. We can do this sort of thing. So if they're dividing, we're subtracting exponents. And I talked about it. If we were doing multiplication of these things, we would be adding the exponents, right? So those are rules that we reviewed a little bit briefly. And where we're at. Find a conversion factor between hectares and acres. Am I tripping? This is like, that is the conversion factor, right? Okay. How many more we got? 3 more? Okay. So using currency conversion, which is more expensive, 5,000 per acre or 10,000 euros per hectare? Okay. So we're going to have to convert one to the other basically on this thing. So which one do you want to convert to which? Are we going to convert to dollars per acre or are we going to convert to, oh, this is acres. That's what the word, sorry. I see what we're doing. I'm being dumb. It's a different word, sorry. 1 hectare is 100 R. Acres. So there's a C in this word. So that's what the key difference is. It might be a little blurry. So I think we got to go back to the conversion. Let me grab that paper. I lost it. It was what, 100? We got 100 hectares per kilometer squared is what we previously got, right? I believe. Someone correct me if I'm wrong. I think that's it. And now I got to go for between kilometers squared and acres. We're doing Jinxmith is not on this one. Let's see if I can figure it out. They got kilometers is I think it was acres. Where's acres? I'm not seeing acres. Do they give us a conversion factor for acres? I don't see it anywhere in this chart. Trying to look. It's not in the 2.2. The 2.3 is just metric. It's not in there. This is where this goes. And they might have given it to us on a previous problem. They give us miles and they give us miles to yards, miles to feet. It wasn't in the notes. They didn't give us any of the notes. Yeah, I don't know where they're pulling acres from because I don't see anywhere on this chart. Well, the good thing is we can go 1 hectare to acres. Oh, that's annoying. We're going to use Google. 1 hectare equals 2.4 acres. So that doesn't look like it's anywhere in the book. So just word of advice. It looked like they wanted you to look that thing up. It looks like I got 2 decimals in there, but it's only 1. Sorry. It should be. Yeesh. So that's the thing they want you to look up. So that we can do this conversion. So if we do 500 per acre or 5,000 per acre for every 1 acre. If we want to convert this to euros per hectare, we need to simplify out the acres. So 2.4 105 acres should go simplify out acres for every 1 hectare. And the other thing here, I need a conversion factor from that table. So going back to the table, I want to go to the euros. There are $1.058 per euro. So one way you can do it is there's that other factor you could use in that table as well. You could be multiplying them. I don't spend a lot of time beating a dead horse. We've had like sort of enough examples. 47105 doing this. So 1.058. Again, we can mark out our units in dollars and dollars, acres and acres, and this should give us in something in euros per hectare. Weird measurement. Don't know anything about these measurements, you might notice, but it doesn't really matter. Like all I need to know how to do is start a unit analysis. This is not dollars anymore. This is euros. So I'll probably round it to 2 decimal places since we're talking about money. Euros per hectare. So if this is 11 and this is 10, which one of those is more? And this one would be so even though it looks less, when you do the conversion, it's going to be more. Are there any questions about this one? We have about 3 more. Okay, use the following facts, exercises, solar photovoltaic cells convert sunlight directly into electricity. If solar cells were 100% efficient, they would generate 1,000 watts of power per square meter of surface area when exposed to direct sunlight. With lower efficiency, they generate proportionally lower power. For example, 10% efficient cells generate 100 watts of power in direct sunlight. Suppose you want to supply 1 kilowatt of power to a house, which is the average household power requirement, by putting solar panels on the roof. If you use solar cells as described in exercise 87, how many square meters of solar panels would you need? Assume that you can make the average power from the solar cells by 4 example, until it's needed. So they're making a lot of assumptions about sort of ideal cases here. But we know we need 1 kilowatt of power. You know, if they're 100% efficient, they generate 1,000 watts. Every 1 square meter. I think they're asking for 87. Let's go. See if I can figure out what the heck they're asking. I don't know, in part chapter 2. So in problem 87. How is it not? Oh, it's because I'm in 2B. Sorry. Oh, why am I being dumb? They're talking about the previous thing. Why didn't anybody tell me that?
Just assume that you knew, Professor.
For some reason, I thought they were talking about the example in the notes in the section, and I don't know why I was being dumb. So, they're saying 100% efficiency will give you 1,000 watts. If we have a 10%, we're doing 10% of 1,000. And they're saying that's going to be 100 watts. But what this sounds like is that we have a 20% efficiency. So ideally that would give them 200 watts. But we know that's using it for 24 hours a day. And we know we're only using it for 6 hours a day. So a 6 is like a quarter of the day. So I still believe we need to divide this thing by 4 to get to, we're going to get 50 watts. We should be getting 50 watts for every 1 meter squared that we have. Is what this thing sounds like to me. It's quite a bit to pick off of this thing. It's quite an elaborate problem. But that's why they give you it for homework, right? So you can take some time to think about it. How many square meters would you need for 1,000 watts is what we want to figure out, or 1 kilowatt. Or we could start with 1,000 watts. So if we want to do 1,000 watts, how many square meters would we need? How would you figure that out?
100.
Shouldn't be 100. We're getting 50 watts per square meter, and we need 1,000 watts. How many square meters are we going to need? What should I write over here? If watts is on top, where should I put watts over here?
Bottom.
Yeah. So this should be the 50 watts per the meter squared. And if we set it up like this, we should end up with something in meters squared. So this should give us our solution. 1,000 divided by 50 should give us, am I doing that right? Should give something that's 2, right? 20. So we should need 20 meters squared. I feel like I'm talking way too much. I need to get a drink or something. Okay, so I think we got that one. Well, that's all of it. Modern wind energy farms use large wind turbines to generate electricity for wind. A typical installation, a single modern turbine can produce an average power of 2.5 megawatts. This average takes the wind variations into account. How much energy in kilowatt hours can such a wind turbine generate in a year? Given that the average household uses about 10,000 kilowatts of energy each year, how many households can be powered by a single wind turbine? So this one is pretty involved as well. We have 2.5 megawatts, and we're going to have to convert what, megawatts to kilowatts, I believe. And the conversion from megawatts. I think might be the first thing that we do. And then we have to go from what? Megawatts to watts, and then from watts to kilowatts. There's a few ways to do this, but if I want to thing. And go from watts to kilowatts. My goal is to get this thing into kilowatts. And if I go look at my chart, there are 10 to the 6 watts. Megawatt. And there are 10 to the 3rd watts. And there are a few ways to do this, but you might notice there's a 10 to the 6 up here. There's a 10 to the 3rd. All in all, maybe I'm going to take 2.5, and I'm going to basically be multiplying it by 10 to the 3rd. There is 3 more that I'm going to increase it by. And so that's looking at these two things, 10 to the 6 and 10 to the 3rd. One over the other, just like that sort of property that we had before. I can kind of look at this thing as 2.5 times this thing, Not looking at the units. I didn't put units on here. No. And hopefully that makes sense because I'm going from megawatts to kilowatts. I'm going from big to small. I should be multiplying or getting larger. I should be moving this thing by, 3 decimal places? 2500 kilowatts is another way to put this. And what was the question I was asking? How much generate in kilowatt hours does the turbine generate? And what was the time again? 2.5. What are they saying? I don't see a time on here. Do you see the time? It says it's an average time of, or an average power of 2.5 megawatts. Are they saying it's yearly? They're not very clear on what they're wording.
So is that 2,500 kilowatts times 300?
This is 10. This would be 1,000.
Oh,
5
1,000.
times 1,000. Yeah.
Oh, Jesus.
10 to the 3rd would be 1,000.
10 times 10. That's 100. Oh, yeah, that's right. 100 times 10 is 1,000. That's what yeah, where I got that from.
I'm confused on why they're saying. Are they saying this is a daily thing? I guess I could look at their solution and see what the heck they're saying. If I go back, there is a odd answers. I don't know, man. This is not gonna, obviously, if I don't know what the heck they're doing. Obviously not expecting to do something this difficult. It's kind of weirdly worded. Let's double check. 2,500 times 365. Yeah, I don't know if they're saying this is per year or what they're saying. They're not very clear. I don't really want to spend much more time on this problem, if I'm being honest. I don't feel like it's worth our time. I feel like we should look at this dosage problem and get done with it. The label on a particular drug recommends 75 to 100 milligrams drug per kilogram of body weight per day. A doctor prescribes 200 milligrams of the drug every 8 hours for a 20-pound child. Is this prescription within the guidelines? Okay, so this one I kind of like because they give us 200 milligrams every 8 hours for a 20-pound child. So we know it's 75 to 50 milligrams of drug per kilogram. What should we do with this child's weight?
Got to convert it to kilograms.
You gotta convert it to kilograms, so pounds to kilograms. We're gonna have to look at that table that goes from metric to standard. So milligram from kilograms to pounds. 1 kilogram is 2.205 pounds. And so we're gonna have to take 20 and divide it by 2.205. But the child weighs something like 9.07 kilograms, somewhere in that ballpark. Okay. And we want to know milligrams per kilograms. So how many milligrams of the drug is this kid getting? And that might be a little tricky part. Because we're doing 200 milligrams. Every 8 hours is going to give us a total of what?
600.
Yeah, we got to do this 3 times a day, is 600 milligrams. So we want to go milligrams per kilogram, drug per body weight. So there's sort of one sort of way that it's going to be milligrams per kilograms, and I think this is probably the only way, right? Drug to the body, that's what we're doing. 600 divided by 9.07, what is that giving us? 66.15 milligrams to kilograms. Is that within the recommended dosage of what they're asking? It looks like he's under prescribing, right?
Oh yeah.
Done prescribed.
Yeah, it's under prescribed. So is that what they're saying? Hopefully. They have it. It's 98. Never mind. Any questions? We're over, like 10 minutes over, I think. But that's 2A and 2B. They are big, pretty big sections. There's something that you should practice, something that you should get to know how to do. 3A and 3B, we're working with percentages and putting numbers into perspective. Any questions over anything? I think that's a pretty good run through of the material for today, I think. 3A should be up. 3B should be up really shortly. The notes are already up. I just got to post up the video.
I have a question on a couple of those questions. The way that you did it, I kind of did it the long way. I don't know why my brain interpreted it when I was reading through the book and looking through your notes. But I still ended up getting the same answer for a lot of the questions, which I did it the long way, but it all evened out somehow. Would I get docked points on the test?
Are you just doing it one step at a time? Is that what you're talking about?
Yes.
Like one conversion at a time?
Yes.
Yeah, that's fine. That's fine.
Yeah, because
It's as long as it's legit work and you're doing it the right sort of way and you're getting it the solution, that's the important part, I think. Hit stop on the recording now. I think this is enough for today.